good afternoon. So, in the last lecture I was talking about catalyst deactivation and then we were talking about the regeneration of the catalyst, which is also very important, and depending upon the catalyst which is used for the reaction, type of reaction and the activity of a catalyst, we need to identify a reactor, a suitable reactor for the process or for the commercialization of the process for the product formation. So, in this lecture I will just talk briefly on the introduction about the various reactors which are generally used for the catalytic reactions. So, basically the fundamentals of the reactor design depends on the various aspects of heat transfer, mass transfer, then reaction fundamentals, and then based on that we select a suitable reactor for a given catalytic reaction. So, selection and design of a catalytic process and the reactor, that depends on process, type of process, that is whether it is a batch process or continuous. So, generally if the small scale production is required, then batch process can be used, but if the production is requirement is large, then either we need to a CSTR type, which is a tank type reactor, or a tubular type, a packed bed type reactor, but both are the continuous operation. So, in the batch the conditions may change inside the reactor with time. So, it is a kind of unsteady state reactor, whereas the plug flow or the CSTR, these are the continuous type of reactor. So, if the catalyst does not decay during the reaction, then we expect that the productivity should not change during the course of reaction. So, that is one of the basic fundamental, either in a homogeneous reactions when you do not have the catalyst, or a heterogeneous catalytic system where the catalyst is used in the process, the reactors may be a batch or a continuous type. So, type of process is one. Then fundamental process variables like residence time, which is very important. So, residence time inside a reactor, when you talk a flow reactor. So, generally in the case of catalytic reactor we talk in terms of W by F A naught. So, this I discussed during the design also, when we have the fundamentals of a plug flow design or a CSTR design, then we call this term as weight hourly space time. So, this is a factor related to residence time known as weight hourly space time, and a very important factor in the design of a reactor or scale up in the scale up process. So, W by F A naught, which is basically W is the mass of the catalyst in the bed, so this is mass of catalyst, and F A naught is the feed rate of the limiting component. So, this is the molar feed rate or mass feed rate. So, basically the units of this you can see here kg of catalyst per kg mass of the feed which is being fed continuously per unit time. So, ultimately it has the unit of time. So, that is why we call it a residence time or weight hourly space time. Sometimes the inverse unit is also used, which is known as F A naught divided by W and called as weight hourly space velocity. So, this is also an important design parameter and especially used in the trickle bed reactors or hydrocarbon process industry, when the superficial gas velocity is used, and based on that the residence time can be calculated or the space velocity can be calculated, which is known as either gas hourly space velocity or liquid hourly space velocity, or if we define in terms of mass of the catalyst in the bed, then this is known as weight hourly space velocity. So, this becomes a very important parameter in terms of the scale up of a reactor or design of a heterogeneous catalytic reactor or even in a homogeneous catalytic reaction. Then of course, the temperature, pressure, because these are the kinetic requirements, and depending upon the reaction conditions we need to identify a definite temperature, pressure, and accordingly the reactor selection becomes important or its design becomes important. Then of course, as I said that during the catalytic reactions we need to consider or we cannot eliminate the mass transfer between the different phases and the properties of reactant is also equally important. So, these resistances which is because of the diffusion, external mass transfer, internal mass transfer, that needs to be considered, and that will also depend on the property of the reactant. So, we need to consider them also for the reactor design. And finally, which catalyst is being selected, that is again in what shape, what size, and what are the properties of that catalyst in terms of the porosity and other structural or geometrical properties, that also becomes very important for selection of the reactor. So, the prerequisite, if you look at for a successful reactor design, are coupling of the actual microkinetics of the reaction with the mass and energy transfer. So, why microkinetics? Because the mechanism of a catalytic reaction is very important. So, microkinetics, when we look at a molecular scale or something like a radicals which form during the reaction or the intermediates which form during the reaction, that should be known. In order to optimize the process or a catalytic process, this microkinetic is also very important. So, one thing is that you get the overall rate of reaction, but when you look at the fundamentals in terms of the design to actually how a reaction takes place on the surface of the catalyst, which is helpful in scale up or in order to remove the undesired product of the reaction, the temperature, that is very important parameter, and other conditions also which can control the product formation, or one can maximize the selectivity of a desired product if that kinetics or microkinetics of the reaction is well known. And simultaneously the dynamics, fluid dynamics, that also influence like back mixing in the reactor, right. So, when you look at a plug flow reactor, and we avoid that kind of back mixing, but in the case of actual reactor we cannot avoid the back mixing. So, we need to find out the residence time distribution or some terms of the flow numbers like Piclet number or dispersion number, which talks in terms of the degree of back mixing, and that term which is a kind of axial dispersion or radial dispersion terms, which are especially in the packed bed reactor, and when you have the length to diameter ratio of the reactor is to be decided. In order to avoid these kind of dispersion, so we need to identify it, which depends, that is depending upon the size of the particle, depending upon the diameter, depending upon the length of the reactor, L by D ratio can be fixed, and we can minimize these kind of numbers, which is the dispersion, that is the coefficient, a kind of non ideal parameter introduced into the reactor design. So, basically what is this? If I just talk in terms of CT by C0 for a tracer input. So, for an ideal plug flow reactor, the everything should come at the same time. So, this is your T by tau base. If I just plot this, where tau is the actual space time or residence time, and this T is the time inside the reactor. So, when some tracer input is given in the reactor in terms of pulse input, and then the concentration is measured, right. So, if this ideal reactor means everything should come at the same time. So, if the everything does not come at the same time, so it is a kind of dispersion. So, that is a kind of non ideal term here, and this is measured in terms of dispersion number. So, this is known as dispersion number, where this is dispersion coefficient and this is the velocity, which is superficial velocity, and L is the length of the reactor. So, this number becomes important. So, for a suppose if I say a plug flow reactor, then this dispersion number should approach to 0, right, or Piclet number, which is LU by D. So, LU by D is known as Piclet number. So, this gives some idea about the degree of dispersion or back mixing in the case of a plug flow reactor. So, we need to consider these studies also, or hydrodynamic studies and residence time distribution in a reactor, in order to understand the flow behavior inside a reactor even under the cold conditions. So, this is just an schematic. If you look at here, the target quantities and influence of choice of catalyst which can affect the reactor. So, we have a catalyst here, we have a reactor system. So, what we expect in the reactor? A good phase contact, we expect unproblematic control in the reactor, the mass flow should be good, residence time distribution should be known, degree of back mixing should be known, heat transfer should be known, that is transport properties should be well known, and operation mode, whether it is continuous, semi batch or semi continuous or batch, that is again important. In the case of catalyst, as we discussed, we expect high activity of a catalyst and selectivity towards a desired product. So, high activity, high selectivity desired. So, chemical properties of the reactants are very important. So, we need to understand their viscosity, surface tension, not only these properties, but other chemical properties also should be known, right, volatility and their the effect in terms of the temperature, pressure, thermodynamic properties. So, everything should be known. Additive effects on the catalyst should be known, stability should be known of that catalyst. So, all these terms, and then based on those we select a choice. So, this choice of catalyst will depend on all these activity and stability and other properties during the catalytic reaction. Then we have to look the chemical activity also, which is mono or bifunctional catalyst, porosity of a catalyst, surface properties, stability of the catalyst, which will depend on the type of support. So, influence of these chemical activity, that is the type of support, catalyst, then it is clubbed in the reactor, and along with the mechanical property of the catalyst, which is also important for the stability of the catalyst. So, it means the optimal geometrical form for high activity, because the mass transfer control reaction, the geometry of the catalyst is also equally important. Mechanical stability of the catalyst, especially when it is a high pressure reactor system, that is important. Mass and heat transport properties should be known, or we should do that study in terms of the energy balance and material balance, in terms of the mass transfer and diffusion limitations, and finally, the stability of the catalyst. So, all these things should be clubbed together for a suitable reactor design. What we look in a design of a catalytic reactor, again, that is whether it is a homogeneous or heterogeneous system. So, the reactor design depends on the process condition, that is the first thing in terms of the temperature, pressure which is required, nature of the reactant, the conversion which is expected, product distribution, that is important, thermodynamics of the process should be known, reaction kinetics in terms of the micro reaction kinetics well known. Then we need to understand the morphological and mechanical properties of the catalyst, which will be placed inside the reactor. Hydrodynamics nowadays becomes very important, which is now the CFD tools are available in order to understand the radial and axial profile and to look at the behavior under the cold conditions. So, flow behaviors during the actual reactor condition, may be a temperature and pressure condition with some say simple cold air water system, or a similar system like hydrocarbons, which say kerosene is if it is used for hydrodesulfurization. So, similar properties can be used in the to study the hydrodynamics under that cold flow conditions. So, physicochemical properties of the system should be same, and one can do the CFD of that and look at the behavior or flow behavior in terms of the non ideal parameters, and that helps in terms of improving the efficiency of the reactor. So, all these terms are important when we look at the reactor design. In general, if you look at a broader classification for a process, so we talk a catalytic reaction based on homogeneous catalysis and heterogeneous catalysis. So, homogeneous catalysis when I say, so of course, the nowadays it is a new trend that homogeneous catalysts are preferred, because the mass transfer limitation or diffusion limitations are minimum in the case of homogeneous catalyst. So, that is why they are preferred, but as I said that separation of a catalyst is difficult. So, still lot of R&D is to be done to develop these kind of homogeneous catalyst system, but once the catalyst is being operated in a homogeneous system, one can very easily use these kind of plug flow reactors, CSTR or a batch type of reactor, depends whether it is a continuous operation or a unsteady state type of operation. So, small scale operation or large scale operation, and accordingly the reactor can be selected. Heterogeneous catalyst, as I said, that is still widely common, and most of the process industry they are using the heterogeneous catalyst, and for that it can be a two phase type where the catalyst is in liquid phase, right, or catalyst can be in gas phase, or it can be a three phase where catalyst is a liquid or a solid, right, or a gas also. So, in the case of two phase packed bed or fluidized bed type of reactors, just like in the FCC cracking I told, the fluid catalytic cracking, the gas and solid system is used, right, and the catalyst a kind of zeolite type catalyst that is used. So, that is a two phase type of system. And if you look at the three phase kind of system, then the trickle bed reactor is especially used for hydrodesulfurization reaction, removal of sulfur from hydrocarbon fraction, which is important for the refinery to reduce the sulfur to a certain level. And in that case, the trickle bed reactors, which are a kind of packed bed reactor at low gas and liquid flow rate. So, I will talk on that later. It can be a kind of CSTR, slurry bubble column reactor, slurry reactor, right, or it can be just a bubble column reactor if it is just a two phase system. So, different kind of reactor systems can be used for heterogeneous catalytic reactions. So, briefly I will talk some aspects fundamentals of these reactors. So, homogeneously catalyzed reaction, as I said, right. So, homogeneous catalyzed reactions, this is something like a catalyst which is present in the liquid phase, if it is the reaction is in liquid phase. So, this can be some metal complex, organometallic complex, right, or something which is in gel form or hydrogel form, that itself acts as a catalyst. So, the idea of nanoparticles, or when we look at a better dispersion of a metal during the catalytic reaction. So, there we get during the homogeneous reaction, we do not have any mass transfer limitation or diffusion limitation into the pore of a catalyst, which is the problem in the case of heterogeneous catalyst. So, in that case, these kind of transition metal complexes, which are basically in the liquid phase, and they are generally a two phase type of gas solid or gas liquid reaction systems. So, gas liquid or liquid liquid reaction systems, right. So, they act as a homogeneous catalyst. The standard reactors again in this case can be a bubble column type or a CSTR type reactor, or it can be done in a batch reactor also. As I said there, because diffusion problem is avoided, and diffusion is a severe problem which because of which the effectiveness factor decrease. So, I was discussing this before, that when we have a diffusion, we were introducing a term rate at any time, or rate in the catalyst is some factor, effectiveness factor times the rate when there is no influence of diffusion resistance. So, that I called intrinsic rate. So, we define effectiveness factor, which is a contribution of diffusion resistance. So, as I told, eta, say it can be something, if there is a strong diffusion, it is something like Thiele modulus phi, right, and phi was defined something like R, say under root of k by d, if I talk a first order reaction. So, just for a first order reaction, if you look at this diffusion coefficient or this Thiele modulus, and generally this Thiele modulus is large number. So, it may be 10, it may be 20 and like that, and because of this your effectiveness factor, if you look at the eta decrease like this as a function of phi. So, when you have high value of phi, so effectiveness factor goes down like this. So, in this case your actual rate, which is your observed rate basically, will reduce drastically compared to the rate where there is no diffusion resistance. So, intrinsic rate means rate when there is no diffusion resistance. So, effectively this is a kind of rate when you have a pellet and you say that there is a diffusion into the pore of the pellet, and because of this the rate. So, here it is some concentration which is CAS, and here it is some concentration like Ca. So, when you have a diffusion resistance, then your concentration profile in a center of the pellet, if I write here 0, right, which is your something like, if I say 0 here, which is the center. So, your concentration profile will drop drastically. So, this is your Ca divided by CAS, if I say, and if 0 is at the center. So, your CAS is 1 here, something like here, right. So, this is your R, capital R radius. So, here the concentration is CAS, and here it is low like this, right. So, the concentration, if you look at here from center of the pellet to this, is going like this, right, or if I just show that, I mean to say there is a drastic drop in concentration from the external surface to the center of the pellet, and if diffusion resistance is more, then your concentration will be very low, and this is the region where you get a low effectiveness factor here. So, it means this when you have a kind of homogeneous catalyst, then you will not face this problem, because in homogeneous catalyst there are no pores, no question of internal diffusion resistance. So, this is the important issue here, that in the case of homogeneous catalyst there are no complexity compared to the heterogeneous catalyst. So, no diffusion problem. So, it means rate will be higher, and that is again that we have a kind of micro emulsion where the rates the catalyst is well dispersed. So, dispersion is not an issue in the case of homogeneous catalyst, because it is a kind of micro structure, a gel kind of, where the particles are well dispersed in the liquid. So, some of the example, if you look at the homogeneous catalyst, is that hydroformylation of olefins in the presence of say cobalt or rhodium catalyst. So, cobalt rhodium complex, basically it is not a solid here, it is a kind of complex which is in solution and reacts during the catalytic reaction. So, what is hydroformylation? Actually it is nothing but the simultaneous addition of 1 mole of hydrogen and carbon monoxide across a carbon carbon double bond, that is olefin, right. So, basically propylene reaction with carbon monoxide and hydrogen, right, to produce a linear and branch aldehydes having one or more carbon atom than original compound. So, basically it is a kind of where the isomers can also be formed, aldehydes can be formed, and this is very important petrochemical reaction if you look at, and there the homogeneous catalysts are used. So, this is a kind of reaction where any olefin reacts in the presence of hydrogen and carbon monoxide in the presence of catalyst, which is a liquid phase catalyst, and the process is basically known as OXO process. So, here you have one linear or normal compound, right, alkene and aldehyde, and then another can be in the form of iso, say butane, right, or butanol alcohol compounds, right. So, it can be high pressure, it can be low pressure. So, hydroformylation of propene to butanols, right, with water soluble rhodium phosphine complex. So, this is the catalyst which is soluble in water. So, the reaction takes place in the liquid phase, and temperature is between 50 and 150 degree centigrade, pressure is between 10 to 100 bar, right, 1 bar is 1 atmosphere, and the concentration of catalyst is between 10 and 100 ppm of rhodium. So, this is the kind of catalyst which you can see here, right. So, it is in liquid phase. So, water soluble compound, right. So, this can also be used for polymerization of ethylene, where the titanium chloride and this aluminum ethyl trialuminate aluminum compounds of this ethylene, which is a kind of Ziegler-Natta type of catalyst. So, they have been used, and that is again a kind of homogeneous catalyst, right. So, these kind of catalysts are used in the petrochemical industry for homogeneous, and the activity of this catalyst is very high compared to the heterogeneous catalyst system. So, this is a kind of the catalyst where is generic rhodium catalyst, where PAR3, that is nothing but triphenyl phosphine or its sulfonated analog, which is used for this reaction, right. And this is a kind of Ziegler-Natta catalyst where the aluminum halides and can be used, titanium halides, aluminum alkydes, and these kind of compounds are used, and they are used for the formation of the HDPE and LDPE type of compounds. So, ethylene polymerization, high density polyethylene, low density polyethylene. So, these type of compounds are produced by using, that is polymerization of ethylene. If reactant definitions, the basically the should be in common, as I said, that a batch is CSTR or a packed bed, right, a packed bed reactor, where you have a tubular type reactor and catalyst is placed in between in the center, and then depends on the mass of the catalyst. So, we have a kind of distributors from the top depending upon the liquid and gas, and to have a better distribution we need to design the distributor. So, a combined, if you look at a reactor design, is very complex, it is a complicated process, but in general, or when you look at just for the catalytic reaction how much mass is required, that simple design be right for the say plug flow reactor design, as I discussed this, W by F A naught is equal to 0 to x a something like this, d x a upon minus r a something like this. So, this is a kind of say rate equation which you get from the writing a mechanism or microkinetic reaction, or one can simply write for simple design Kca to the power n and find out the mass of the catalyst for a given production or for the conversion, given conversion, say 90% conversion, with how much feed is being used and what will be the productivity, or one can write these expressions, and this is a kind of plug flow reactor design. If it is CSTR or a tank type reactor, then one writes simply W by F A naught is equal to simply X A upon minus R A dash. So, one can very easily find. So, this is for a CSTR or tank type. So, even if you write a bubble column or a fluidized bed reactor, under simplest condition one can assume it like a CSTR, right. But if you look at the actual design for a fluidized bed reactor, you need to look at the 3-phase model or 2-phase models, right, to find out these rate equations, because there will be a limitation of mass transfer, right, and accordingly one needs to consider the overall rate of reaction, which includes the resistances for mass transfer also in different phases. So, these are the very common design expression for a ideal plug flow reactor, and this is for this CSTR reaction, right. And similarly, in the batch reactor one can find out the time for a given conversion, and which is again time for given conversion is equal to N A naught times 0 to x dxa upon minus R A into R A dash if I write, so into W. So, one can write the expressions like this, which is similar to a plug flow reactor expression, where only W by F A naught is replaced by something like a term which is your flow rate. So, here T is written in terms of that, because the batch is unsteady state operation and condition change with time on stream. So, this is the time required for a given conversion in a batch with this the moles which have already been kept, because in the batch there is nothing like a continuous flow. The reactants are fed inside, and then after certain time we get the product and we measure the conversion by analyzing the components. So, these are simple design expression, but when you look at the actual design, reactor design, we need to correlate these in terms of the hydrodynamics, that is, as I told, that CFD type expression, or look at the cold flow conditions and then evaluate the mass transfer effects also, and then include it into an overall rate expression, right. So, it means the effect of particle size will be important, the flow velocity will be important, and that needs to be incorporated in the actual reactor design. So, if you look at the definition wise, the reactors, various reactors which are used in the catalytic process industry. So, packed bed reactor, which is very common, as the name says, the something in a tube and you pack it, right, with the catalyst. So, gas or liquid reactants flow over a fixed bed of the catalyst. So, you have a bed and you pass the liquid or gas co-currently or counter currently. So, something like this, there is a bed where you have put the catalyst, right. You have ensured that there is a proper distribution, right. So, you have to make the condition that there should not be any channeling, right. Channeling, this may happen that the gas pass through the bed like this, right. So, this is to be avoided. So, sufficient amount of inert is to be packed here, right, from top and bottom like this, and you need to put, look at the size of the particles also, and these catalyst particles should be mixed with sufficient amount of inert also, especially when the reaction is endothermic or exothermic. So, that the heat transfer, heat should be dissipated. So, depending upon the type of the reaction, one needs to look at this also design. And again, this height of the bed is important, which I told L, right. The diameter of the reactor is important, diameter of the catalyst is important, size of the catalyst. So, all these factors should be considered, right. So, you need to have a large length to diameter ratio, a large length to this diameter ratio, right, and a definite d by t ratio also to avoid the channeling, that is wall effect. Otherwise, when you have a liquid, it has a tendency to move towards wall. So, there will be more wall flow. So, you need to decide these factors depending upon the hydrodynamic study, and these are very important when you look at the actual reactor design or when you model the reactor. We need to introduce those terms or non ideal parameters in terms of the axial dispersion, radial dispersion, like that terms. So, this is one. The same thing can be done in a fluidized bed reactor also, right. So, fluidized bed means something where the solid is acting like a fluid. right. So, small particles, these are the small particles which are fluidized or in fluid medium or bubbling media along in the presence of some gas. So, some carrier gas may be required to keep the particles in the suspension form. So, what is the advantage? Advantage is that now every particle is available for reaction, catalytic particle is available for reaction, where here it may happen that the pressure drop is an issue, right. The particles are packed tightly. So, there may not be any voids between the particles, right. So, the pressure drop will increase, but in the case of fluidized bed the pressure drop is less, right, and you can have better contact between the gas and solid or reactant and the catalyst. So, that is some advantage, there are some advantage with this fluidized bed, but of course, because the distribution is poor now, there will be a more back mixing, because when you look at a packed bed reactor, we resemble it with a plug flow reactor. So, in the plug flow reactor there is no back mixing, right, there is no back mixing at all. So, so concentration, if you look at in the longitudinal direction, that is it is decreasing down the length of the reactor, but in the radial direction it is a uniform throughout. But in the case of this fluidized bed, there will be a kind of back mixing. So, it means you need to find out the residence time distribution, right, because it is not like an ideal reactor. Basically, plug flow reactor, if you compare it with the fluidized bed reactor, so fluidized bed reactor is behaving like a CSTR, right. So, when you have a circulating fluidized bed reactor, it gives a higher conversion, because it will resemble to some extent to the plug flow reactor, right. So, this is what the design aspects we have discussed here, right. And CSTR, again CSTR can be used just like a bubble column reactor, right. So, gas liquid contact. So, liquid and gas phases are mechanically agitated. So, it is a kind of agitated bubble column reactor also, which is again a kind of tank reactor. So, you have a gas or along with the liquid, or if you can do gas can be bubbled from the bottom, right, and then liquid is already in the bed in the column, right. So, that is a bubble gas liquid bed reactor. So, both are similar in one way, right. So, this here the liquid and gas phases are mechanically agitated. Here the bubble gas liquid bed, the liquid phase is agitated by the bubble rise of the gas phase. So, bubble size becomes important here, because smaller the bubble size, the mass transfer coefficient will be very high. So, it is a kind of the system where if you have a solid also, it becomes a 3 phase kind of reactor. So, we need to look at the mass transfer, solubility of the gas and liquid, and then accordingly the design or size or sparger design, so many things, or stirrer, agitator speed, all these things should be fixed or identified for the design of a reactor. Then we have a bubble column reactors, right. So, so again if you look at the example here, the homogeneously catalyzed air oxidation. So, this is a kind of example of homogeneous catalyst in a bubble column reactor. So, homogeneously catalyzed air oxidation of hydrocarbon like toluene, benzene. So, basically this process is done for the reduction of the pollutants. So, it is a kind of wet air oxidation, right, in the presence of some homogeneous oxidizing catalyst like hydrogen peroxide, right. So, toluene to benzoic acid, temperature is around 130 to 150 degree centigrade and pressure is around 1 to 10 atmosphere. Manganese or cobalt salts are used as a catalyst, they are soluble in that. So, it becomes a homogeneous system. For the same case, heterogeneous catalyst can also be used. So, it is an example of homogeneous catalysis and done in a bubble column reactor. But when you have solid catalyst, it becomes a kind of trickle bed reactor. So, we will talk on that. Same thing for oxidation of xylene to terephthalic acid over cobalt manganese salts and bromide at 100 to 180 degree centigrade and 1 to 10. So, these are some examples where we can use a bubble column reactor using the homogeneous catalyst. Again oxidation of ethylene to acetaldehyde. So, this can be done in the presence of palladium chloride and cuprous chloride. Just if you look at design equation which I have already talked, basically this is your a heterogeneous catalytic reactor design if you have a kind of packed bed reactor. So, this is what the mass of the catalyst divided by the feed rate, right. It can be a molar feed rate or the mass feed rate. So, this is the same expression which I have written in the form of W by FA naught, and since I told you that plug flow reactor the condition change down the length. So, this is our plug flow reactor and we are taking a differential element here, and for this we are writing our mole balance equation, right, and this is the delta Z or dZ in the reactor, which can be written in the form of del. So, this is your area of cross section into dZ. So, that is your volume of this section, right, and if you multiply with the density of the catalyst, which is bulk density. So, that is your mass of the catalyst in the bed, right. So, this is your W, mass of the catalyst, which is in differential section in this. So, when you write a mass balance, so something is going in from here F A and something is coming here at this distance Z plus delta Z. So, you know your material balance, that input minus output minus disappearance because of chemical reaction within this system. So, that can be written R A dash times d W if I write in terms of mass, right. So, mass in or moles in minus moles out minus disappearance because of chemical reaction is equal to 0 because it is your steady state reaction. So, one can very easily write this equation, that which is simply here dFA by dW, right, minus dFA by dW, or dFA by dW is equal to minus R A dash, right, or that is what I have written FA naught dXA by dW is equal to minus R A dash, right. So, this is your differential form of reactor design equation, and that expression, because when you write for whole system. So, here it is 0 to W, total mass of the catalyst required to achieve a given conversion X. So, one can very easily integrate this, because in this case this is simply your integration becomes, which is your F A naught dXA, right, is equal to minus R A dash times dW, this equation. So, we have simply integrated this now 0 to X A, because your inlet conversion is 0 and it will change to final conversion X, for which we are calculating our mass of the catalyst dx, and since R A dash will be a function of conversion. So, we take it here, right. So, R A dash is your rate of disappearance, which will be function of conversion, right, or concentration, is equal to 0 to W, total mass of the catalyst dW. So, this is simply your W, and F A naught is already here. So, that is what W by F A naught is equal to 0 to X A dx upon minus R A overall plug flow reactor design, and that equation is written here, and this is the differential form which I was talking for a differential element. So, once you have a small reactor, a plug flow reactor in differential form, that behaves like a CSTR, right, which is the design equation for CSTR when we reported here in this case. So, this is a CSTR design equation, total mass. If I write it for a differential form, this becomes dW, right, dx. So, it means nothing but the PFR is nothing but infinite number of CSTRs placed in series, right. So, this is what the size of a reactor sizing. So, you can see here that 1 upon minus R A, which is from here in this equation, right. So, dx upon 1 minus R, this is your x conversion down the length of the reactor and reported as a function of R A, 1 upon R A, right. So, it means for a plug flow reactor, if you take the area under the curve, this area, this is your integration 0 to x dx upon minus R A. So, minus R A I am writing because it is disappearance of the reactant. So, this is for a plug flow reactor, that area under the curve is your W by F A naught, right. So, this value can give you easily the mass of the catalyst required for a given conversion. But if you look at a CSTR, in the case of CSTR, W by F A naught is not the integration, but x divided by minus R A. It means the area of this rectangle will be your W by F A naught, right. So, for same feed rate or for identical conversion, you can see here the volume of CSTR or the mass of the catalyst required in a CSTR will be much higher compared to a plug flow reactor. So, plug flow reactor is better in that way, because the concentration is changing down the length and you are measuring the rate along that, whereas in the case of CSTR, the concentration we assume that immediately drops to the final value. So, that is the similar to the homogeneous reaction. When you studied that, we use the same terminology here in the case of heterogeneous catalyst also, that when you have a CSTR and you want to achieve the same conversion like in a plug flow reactor, then you need to increase the size of the reactor, or you need to use the larger mass of the catalyst in the reactor. Just as an example for exercise, I have just taken a problem here which is nothing but a simple design, and we have said here that there is a reaction between A and B which are in gas phase and transforms into a product R and S. The molecular weight of these reactants are given, right. 80, A has 80, B 20, R 60 and S 40. The A and B are fed in stoichiometric proportion, that is equivalent to their this 1 mole of A reacts with 1 mole of B and gives 1 mole of R and 1 mole of S. So, this is what given here in this case. The product which is formed here, just a minute. So, this product A plus B gives you R plus S, and they are fed in the stoichiometric proportion to the reactor. The rate law which is determined from the mechanism of the reaction, and that is given in the form of Langmuir-Hinshelwood type mechanism. So, this is given here in the form of Langmuir-Hinshelwood mechanism, which is K1 times Pa times Pb divided by 1 plus K2 Pa plus K3 Pr. So, that has been given because we have discussed this earlier. When we write this kind of mechanism, we say that there is the adsorption of A on the catalyst, there is adsorption of B on the catalyst, and then they transform into some adsorbed R species and S species in the surface reaction, and then finally this product desorbs. And assuming surface reaction is the rate controlling, we write a mechanism, right, and there can be different kind of postulation which we already discussed to derive the rate, which is a Langmuir-Hinshelwood. So, here this has been mentioned that rate is proportional to the partial pressure of A and partial pressure of B, and species A is adsorbing on the surface, but not B. So, B is in gas phase basically, and PR is adsorbing, not the S. So, one can very easily write the mechanism and derive this kind of rate equation, which I am not discussing at this point. We assume that from the rate equation, this kind of from the mechanism, the rate equation has been obtained and rate parameters have been evaluated like this. So, the rate parameters which can be determined experimentally by regression analysis. So, K1 rate constant is given, which is this, K2 and K3 are equilibrium constant, right, and the values are given in terms of 4.5 bar inverse and 41.6 bar inverse, right, for the equilibrium constant. So, what you have to do, you have to find out the mass of the catalyst to achieve a conversion of 80% in a packed bed reactor, and compare the same mass or mass of the catalyst required in a CSTR. So, the same thing which I have discussed here now is given in the form of problem. So, it is a simple problem, and I hope all of you can do, because you have to just write down this is the stoichiometry. So, one can say that if 1 mole of this is reacting, 1 mole of this will react, and 1 mole of this will form, and 1 mole of S will form. So, we need to find out Pa, Pb and Pr in the form of X, right, because our reactor design equation in a packed bed reactor will be this one, W by Fa naught is equal to 0 to x dx upon minus Ra dash for a plug flow reactor or packed bed reactor, assuming plug flow condition. So, we need to find out the mass of the catalyst. Fa naught is the molar feed rate of the limiting component. So, since they are given in the stoichiometry ratio, so you can take either, right, and A is your, let us take A as Fa naught, molar flow rate of A. Ra dash is given, only thing that we need to transform these Pa and Pb in terms of x for integration, right. So, we made a kind of stoichiometric table here, right. So, that is at any time when the conversion is x, right, the moles fractions we can write, right. So, we have seen that there is no fractional change in the volume. Otherwise, we need to write the expression for concentration in terms of C A is equal to C A naught 1 minus x divided by 1 plus epsilon x, right, where epsilon is fractional change in volume. So, fractional change in volume during a reaction. So, that is basically final volume minus initial volume divided by initial volume. So, suppose the reaction is given here, in this case is A plus B gives you R plus S. So, here 1 mole of this, 1 mole of this. So, initially 2 moles are reacting because there is no inert and 2 moles of this will form, right. So, in this case epsilon is 0 because there is delta is 0, delta is difference in the stoichiometric coefficient of the product and reactant. So, 1 plus 1 minus here again 1 plus 1. So, this is 0. So, delta is 0. So, epsilon which we define based on Y A naught, that is mole fraction of the limiting component, times delta. So, since delta is 0, so this becomes 0. So, in this case your C A is simply C A naught 1 minus x, right, and you know C A is equal to P A divided by R T. So, in some cases you may be given the concentration data. So, one can substitute either in terms of concentration or in terms of partial pressure of A, and partial pressure can also be written total pressure multiplied by mole fraction of the component. So, in this case if you look at here, we have the stoichiometric table, because if 1 mole of A has entered, so x mole reacted. So, at any time t or given conversion, it is now 1 minus x. Since 1 mole of A is stoichiometrically fed, so 1 mole of A is fed. So, 1 mole of B will be also fed, right. So, again moles of B left is again 1 minus x, because partial pressure at any time, right, when we talk down the length of the reactor, here in the case of the time meaning at any length of the reactor Z, right. 1 mole of A reacts, so 1 mole of R will form, right. So, this is x reacted, so x will form, and similarly 1 mole of A reacted, equal number of S will form. So, x moles are also x, right. So, this is the total moles. So, partial pressure you know at any time, because P A P B is to be substituted. So, partial pressure is total pressure into mole fraction, right. So, here you can see that total moles are again the same, there is no change in the number of moles. So, this becomes partial pressure of a P A naught, which is P A, right. So, that is again 1 minus x, otherwise it is P A naught into 1 minus x, you can calculate that, right. Same thing for P B, and this is increasing. So, this is x and this is x. So, these values of P A P B, P R P S will be substituted in this expression. So, this is the rate equation which has been determined. So, substitute the value of P A, P B and P R here. So, now you have K 1 P A into P B. So, P A is equal to P B here. So, 1 minus x whole square divided by 1 plus K 2 P A is again 1 minus x plus K 3 times P R, which is x. So, this is your rate as a function of conversion data. So, K 1, K 2, K 3 all are known. So, we have substituted these values here, right. So, now F A naught, F A naught is the molar feed rate of A, right, and you know that the production desired is mentioned here is 10 ton of R per day, right. So, 10 ton of R per day is to be produced. So, in a reactor design, to produce 10 ton of R, how many moles of A are required to achieve a given at a given conversion level, one can find out. So, that is written here, right. So, if the conversion desired is x, so F P, which is the product desired 10 ton, divided by x will be the moles of A which is to be fed, right. So, this is the moles of A fed. So, that is 10 ton divided by this is given in terms of per day. So, we have converted it in terms of hour, right. So, conversion level given is 80%. So, x is 0.8. So, this is hours in a day, and this is number of day into multiplied by 60. So, total number of hours, and this is conversion. So, roughly it is 8.7 kilomole per hour of A. So, now this value will be substituted in this equation, which is your W by F A naught is equal to 0 to x dx upon minus R A, right. And so, this equation can be solved analytically. If not possible, then one can use any ODE solver also, right. So, any ordinary differential equation solver or in MATLAB, Polymath, it can be solved, right, and one can use the numerical methods like for Simpson's rule, which you have read in your homogeneous catalytic reaction also, or any mathematical course. So, the one can use either MATLAB or Polymath or any other software for solving these kind of equations or integrating this numerically. So, this is roughly, if you do that, you get 1615. So, please check it and you can practice it at home, right. For CSTR, I told you need not to integrate, the conditions will be calculated at the exit of the reactor. So, for CSTR, W by F A naught is equal to simply X A divided by minus R A dash calculated at 80% conversion. So, this just substitute here x is equal to 0.8. So, rate can be calculated, and F A naught you have already calculated here. So, W is equal to F A naught times X A divided by minus R A. So, this comes roughly 10,260 kg. So, one can see that a large amount of mass of the catalyst is required in the case of tank type reactor, because there is a degree of back mixing, right. So, one can compare. So, plug flow reactors are always better in terms of, means better means for most of the reaction when you look at smaller mass of the catalyst or smaller size of the reactor. So, very quickly there are different type of reactors which are used in the process industry. If you look at here, the one is your just like a packed bed reactor or a fixed bed reactor. So, we call it single bed reactor. So, there is only one bed of catalyst. So, especially the selection depends on the deactivation performance of the catalyst, the conversion level which is desired, endothermic, that is the endothermicity, exothermicity of the reaction. So, which will depends on the heat transfer, right, that will decide the reactor design, how the heat can be removed from the process, or it can it be adiabatic, isothermal, non-isothermal type of reactors. So, though the different names have been given or different type of design approaches have been given depending upon the heat transfer, mass transfer, and so mass balance, energy balance, momentum balance for pressure drop calculation. So, all these things should be checked for the commercial reactor design. So, the single bed reactor, if you see here, it is the simplest catalytic reactor, because it is a kind of fixed bed reactor, as I said earlier, and deactivation should not be a big issue, then only it can be used. So, it is completely filled with catalyst and is mainly used for thermally neutral and autothermal gas reaction, right. So, because in the here the heat removal should not be an issue, otherwise hot spot formation may occur. So, that time this reaction may not be good. So, those reactions where the heat generation term is negligible, we can prefer a packed bed or fixed bed type of reactor. So, owing to its design, the pressure drop is high. So, as I said, it is a kind of packed bed reactor, right. So, voids, if your particles are fine, very small powder type particle, then the pressure drop will be excessive, right. So, energy loss will be there. So, and the residence time distribution has the major influence on the selectivity and conversion. So, RTD becomes very important. We need to look at the residence time distribution, right, cold flow conditions, flow visualization. So, maldistribution to be avoided or kind of distributors to be designed. So, these things should be looked into, right. So, that is why the pressure fixed bed reactor or single bed reactor may not be very good, right, when the reaction is highly exothermic or when the particle or catalyst is in powdered form. So, of particular importance in this type is the maintenance of the temperature limit both axially and radially, as heat removal is naturally poor. So, in this case heat removal is an issue. So, if the reaction is endothermic or exothermic, this should not be used, right. So, this reactor is only used when the reactor is isothermal and very large particle size, large size of catalyst particles are used in the bed, so that the pressure drop should not be an issue. But the advantage is that it is the catalyst can be regenerated easily, because generally the deactivation is not an issue in this kind of reactor, but you can shift it to some another reactor and regenerate it and again take it back. So, the maintenance problems are very low in this kind of reactor or less. So, some of the simple reaction like isomerization of light gasoline, which is done generally at 400 to 500 degree centigrade, pressure around 20 to 40 atmosphere in the terms of hydrogen pressure, and catalyst is platinum alumina catalyst. So, that is done in this single tube reactor. Catalytic reforming of solvent naphtha, which is again a cascade of 3 to 5 single bed reactors. The temperature is 450 to 550 degree centigrade, pressure is 20 to 25 atmosphere in terms of hydrogen pressure, and chromia, alumina, potassium oxide catalysts are used. So, these are some examples of the catalysts or reactors which are where the single bed of the catalyst can be used, and say another example is your hydrocracking of heavy hydrocarbon, where again the temperature is around 400 to 500 degree centigrade and the pressure is 20 to 60 bar of hydrogen, and oxidic or sulfidic hydrogenation catalyst like molybdenum tungsten, cobalt tungsten on alumina or silica supports are generally used. So, these are some of the reactors or some of the reactions where this kind of catalyst can be used in the process. So, I stop here and thank you for your attention.